got 1.05, let's call it 0.6 times 10 to the negative 9.
Okay.
Cool.
Good deal.
So now we know that this value, well, both of them have the units of newtons. That value is going to apply to our vertical vector and our horizontal vector.
Uh-huh.
And then this one will apply to just our diagonal.
Okay.
Great, so now what do we do?
So, what we're looking for is the magnitude of the gravitational force exerted on one sphere by the other three. So we need to know how much the pull is by all three of those.
Right. So right now we've got a free body diagram showing three individual forces. We want to know what the total sum of all three of these things are.
Let's just add them up.
Yeah, we can add them up, but we can't just add them up, by adding this plus this plus this, because they're not all in the same direction.
Right, okay.
So what we need to do is we need to take this diagonal vector, and this is what we always do with diagonal vectors.
Okay.
If we have a vector that's on a slant, it's not lying right on an axis, we always want to split it into components.
Okay.
So we are going to say, well, we know that this vector is really just this vertical vector plus this horizontal vector. And that makes a right triangle. So we know the hypotenuse has the magnitude of that. And we know that this is a 45-degree angle right in there. And so using sine and cosine, we can figure out the magnitude of the or the y component and the magnitude of the x component. I'm sure you've done that loads of time, right?
Okay. Yeah, we've found the x component and the y component. So let's see here, I'm just looking at this. So the top one would be a 90, the one with the square. And so a 90, it all has to add up to 180, so that the other two have to be 45s, right? Is that what we were saying?
So this 45 came from knowing that with a square.
Oh yeah, that's just coming from half of 90, right?
Right. So we know that this is directly in the middle between these two.
Right, which is 45. Okay, that makes sense.
So yeah, that didn't require too much math. That's just kind of knowing that if you take the diagonal of the square, it's always going to be a 45-degree angle.
Okay, good.
Cool. So 45-degree angles are nice because once we find the magnitude of one of these sides, we know the other side is going to be the same.
Okay.
So if we say, let's do sine for example, we can say sine of our 45-degree angle is equal to our opposite side, so that's that guy, so we can call that our x component, divided by our hypotenuse, which is 1.06 times 10 to the negative 9. So now we can algebraically just solve for that x.
Okay. So you got 7.5 times 10 to the negative 10.
Perfect.
Good deal.
Great. So now that we've got this diagonal vector split into components, we can come down here and we can draw like a new free body diagram. So we know that we've got one of our y components is 2.11 times 10 to the negative 9. We've also got this other y component that we can add to it, and that's the 7.5 times 10 to the negative 10.
Oh.
And then in the x direction, we have this guy plus that guy.
Gotcha. Okay, so you just add them up.
Yeah, that's the utility of splitting it into components, because now we can just add.
That's
because
awesome.
they lie in the same axis, they point in the same direction.
Okay.
Whereas before, you can't add that number to that number because they're not in the same direction.
Okay. So you add the individual vectors of the different components.
So now we end up with both of these being equal to 2.86 times 10 to the negative 9 newtons.
Okay, sweet, yeah. So that'll be the X, that's the X, and then the Y is 2.75. Sorry, I'm just trying to make sure you get all these notes so that I can have it for later. Plus our other Y, which was
2.11 times 10 to the negative 9.
Just realized I just. Oh, so the one up was 1.06, is that right?
Yeah.
Okay, I wrote down the wrong thing, so I'm glad that I fixed that. 1.06 times 10 to the
Oh wait,
negative
maybe I don't understand what you were asking.
9. So let's see, the one that we solved for our original, so there's 2.11 was the up, and then the over.
Yep, those are the same. The diagonal one was the 1.06.
Oh yeah, okay, so that I did have it right. I'm sorry, I was thinking that we had different values for those, but they were the same.
But yeah, the 1.06 times 10 to the negative 9, we just forget about that because that's not a useful number. What's useful is knowing what its x and y components are.
Gotcha. Okay.
And so instead of thinking of it as one diagonal vector, we think of it as two component vectors.
Gotcha. Okay. Yeah. So then you added those up for the x and the y, and you got the exact same value for both.
Yep, because that number was the same for both, and then that number was the same for both.
Oh yeah. Okay, that makes sense. Cool.
So then we end up with both of them being 2.86 times 10 to the negative 9. So now we want to find the resulting vector.
Okay. That makes
So
sense.
we know it's going to be, something in this direction. So we know it's going to be at a 45-degree angle again, and we can solve for it mathematically because we can see if we just pick this up and move it over here in our mind. Then we've got this right triangle. We know that this side of the triangle is 2.86 times 10 to the negative 9. And so is this triangle, or this side.
Yeah.
So we can do a squared plus b squared equals
C squared.
c squared.
Gotcha. Okay. Cool.